Welcome back to the Deep Dive. Today, we're digging into something pretty fundamental, actually. It's about how AI is learning, but maybe not in the way you usually think about it.
Right.
We're moving past just feeding it data into this realm of, well, custom-built training grounds. We're going to explore these machine-readable 3D worlds. Sounds intriguing, right? Our plan today really is to sift through the latest thinking, the research, the expert takes, and pull out the key stuff for you. Think of it as your quick guide to understanding what this is all about, why it's a big deal, and, where it might be going.
Yeah, and it's more than just like a technical curiosity. This is really foundational stuff we're talking about. These environments are basically paving the way for AI that's more robust, safer. It's about building smarter systems right from the start, and, well, that affects everyone, really.
Okay, so let's try and get our heads around this. A machine-readable 3D world. What does that actually look like? I mean, is it just a fancy video game? Or is it something more?
That's a really good question, and it's key. Think about playing, say, a driving game. The computer, and you as the player, you mostly see the graphics, right? The visuals on screen. It processes the shapes, the colors, the textures, but it doesn't automatically know the deeper meaning behind those pixels.
Right, and that's where we humans have this huge built-in advantage. We've walked around real cities, we've interacted with real objects. So when we see a virtual street, our brain just connects the dots. We know what a car is or a building. We're drawing on like this massive internal library of experience.
Exactly. We infer meaning. Machine-readable world, it makes all that inference explicit for the AI. In these special virtual worlds, every single thing, every object, surface, even the rules like physics, is all clearly listed out, defined in a big digital list. And the computer can just read that list directly. It's not guessing from pixels. It knows what the pixels represent. Fundamentally.
Okay, that is a big shift. It's not just seeing, it's knowing. Can you give us a really concrete example? Like, what does that explicit list look like for an AI encountering, I don't know, a cup?
Sure, perfect example. So imagine a simple blue cube in this world. In a normal simulation, the AI sees blue, sees a shape, and has to figure it out. Is it a box? A weird cup? But in a machine-readable world, the environment literally tells the computer, okay, this is object ID number 342. It's category, that's cup. Material, porcelain, weight, 0.2 kilograms, and its exact spot is at coordinates, 2.3 meters, 1.1 meters, 0.5 meters.
Yeah.
No ambiguity, no guesswork involved. The AI just knows.
It just gets the facts.
Precisely. And this kind of explicit, clear information is, well, incredibly valuable. It lets AI systems learn much, much faster. And maybe even more importantly, they can learn more safely within these controlled environments because everything is perfectly defined. No surprises.
So knowing that, it really clicks why researchers are pouring so much effort into this. What are the big game-changing wins here? Why is this approach seen as so, well, revolutionary for training AI?
Well, you can think of these worlds as like supercharged training grounds. Really efficient. They make the whole learning curve much smoother, much more targeted. One of the biggest benefits is something we call free, perfect data. Think about training an AI to spot chairs in photos. Normally, you'd need humans. Lots of humans, drawing boxes around chairs and thousands, maybe millions of images, labeling everything. It takes ages, costs a fortune.
Yeah, that's the bottleneck we always hear about, the data labeling nightmare.
Exactly. But in a machine-readable world, the computer instantly knows which pixel belongs to which chair leg, which bit is the seat. The labels are just there, perfect, free. No human needed for that part.
And the knock-on effect of that must be massive.
Oh, huge. It doesn't just save time and money, though it definitely does that. It kind of changes the economics of training complex models. Suddenly, scenarios that were too expensive to label manually become feasible. It opens things up.
Right, so it's faster, cheaper, and maybe even more accessible for different research groups.
Definitely more accessible. Another really key advantage is quick testing and debugging. Imagine you're training a virtual robot arm, and it keeps knocking stuff over. Why? In a normal sim, figuring that out could be tricky, but here, the world can tell you exactly what went wrong, like, oh, the friction value on that virtual table, it was set too low, or the robot misjudged the table height by 5 centimeters.
You get immediate, specific feedback, less guesswork in fixing problems.
Precisely. Cuts down debugging time like you wouldn't believe. And then there's the ability to create really tailored learning experiences. You know how a good teacher starts simple and builds up? You can do that here. Start the AI with really easy tasks in a simple version of the world, then gradually ramp up the complexity as it improves. It's adaptive learning.
That makes a lot of sense, sort of like starting with kindergarten before going to college. And I guess safety is a big piece of this puzzle, too.
A massive piece. Safer development is absolutely critical. Think about a robot learning to cook in a real kitchen. One mistake can mean a fire or broken dishes or worse, but in a virtual kitchen, it can mess up thousands of times, burn the virtual toast, drop the virtual eggs. No harm done.
It's a completely safe sandbox to fail in, essentially.
Exactly. Learn from mistakes without any real-world cost or risk. And one last big one. Easier transfer to the real world. This is sometimes called the sim-to-real problem. By being really careful about matching the virtual world's physics, the massive objects, the slipperiness of surfaces, how things bounce to actual real-world measurements, the skills the AI learns in the simulation are much more likely to actually work when you put that AI brain into a real robot body.
Wow. Okay, when you lay it all out like that, the perfect data, the fast debugging, tailored learning, safety, better transfer, it really does sound transformative.
Yeah.
It feels less like tweaking the old methods and more like a genuinely new, more engineered approach to building intelligence.
Yeah.
Faster, safer, probably more reliable in the end. But it sounds almost too good, like the perfect solution. As with anything this advanced, there've got to be some major hurdles, some big challenges researchers are wrestling with. It can't be all smooth sailing, can it?
No, you're absolutely right. It's definitely not all solved. These are very much active research areas, big questions people are working hard on. One of the biggest challenges is keeping things realistic.
Yeah.
See, a world that's super easy for a computer to read with everything neatly labeled might end up looking a bit, cartoonish. Or the physics might feel a bit off, a bit too simple.
Right. And if the AI only ever trains in that kind of perfect, maybe overly simplistic world, what happens when you drop it into our messy, unpredictable reality?
Exactly the problem. It can struggle. The real world doesn't come with perfect labels on everything, and its physics are incredibly complex, chaotic sometimes. That gap between the clean simulation and messy reality is a major hurdle. Then there's just the sheer complexity and size of these worlds. Think about modeling just one detailed virtual kitchen. You could have thousands of objects, every spoon, every spice jar, every apple.
Wow.
And each one needs that whole list of properties. What it is, what it's made of, how much it weighs, exactly where it is, just storing all that data, keeping it updated, rendering it. It's computationally very, very expensive. The data density, as you said, is immense.
Okay, that makes sense. It's a data management nightmare, potentially.
Potentially, yes.
Yeah.
And another big issue is that different groups are building their own worlds using different languages, so to speak, different data formats. One group might call an object a cup, another might call it a mug, one might report physics impacts differently than another.
So it's like everyone's building their own little universe with its own unique instruction manual. That must make it really hard to share findings or build on each other's work.
Precisely. It fragments the research community. Sharing models, replicating results, collaborating effectively, it all becomes much harder when everyone's using a different format or standard. It definitely slows things down overall.
Okay, what else?
Well, there's the cost of building good worlds in the first place. Creating high-quality, realistic 3D models and meticulously adding all that machine-readable data. It takes a lot of time, specialized skills, 3D artists, physics experts, and frankly, significant financial investment. These aren't cheap to make.
So accessibility is still an issue, even if the data labeling part is easier.
Right. And then there's a more subtle challenge, keeping the virtual world honest. There's a risk. What if the AI, while learning, figures out how to sort of cheat, how to manipulate the simulation's rules in ways that wouldn't work in reality?
Like making a wall invisible just to get through it.
Exactly like that. If the AI learns those kinds of simulation hacks, they're completely useless, maybe even dangerous, when it tries to apply them in the real world.
So you need to make sure the AI can't just game the system, that the learning environment stays true to the rules you intended. That sounds tricky.
It is. Maintaining that fidelity, that integrity of the simulation is crucial. And lastly, there are often privacy and ownership issues. Many detailed 3D models, especially really good ones, are proprietary. They belong to companies. Sharing the full machine-readable description, which includes all the underlying data about that model, can get complicated legally. Who owns what? Can it be shared for research? It's not always straightforward.
Goodness, that is quite a list. Realism versus readability, complexity, different standards, costs, preventing cheating, ownership. It really highlights that this isn't just a technical problem. It involves standards, economics, even legal frameworks. It sounds like a really delicate balancing act.
absolutely is. Balancing that visual realism with the need for clean, explicit data is key, and getting everyone to speak the same language is a huge ongoing effort.
Okay, so we've gone through what these worlds are, the really powerful benefits, and also these significant ongoing challenges. Let's try to bring it together. What's the sort of bottom line for someone trying to understand this? How should we think about it? And looking ahead, what's the promise?
Well, the core idea, the takeaway, is pretty straightforward, I think. Machine-readable 3D worlds are basically these incredibly detailed virtual playgrounds. But the key is every single thing in them, its name, shape, weight, how it behaves, it's all written down explicitly for the AI to read and understand directly. And that gives the AI this massive shortcut. It gets perfect data instantly, it can practice dangerous tasks safely, and it gets lessons tailored exactly to its level. It's a bit like giving a student a magical textbook that not only has all the answers, but also gives instant perfect feedback on every single exercise they do.
That's a great analogy, the magical textbook.
Yeah, and because of that, it really does speed up the development of AI that's more capable, more robust, hopefully much more reliable and safe in the long run.
And looking out, say, 5, 10 years, what's the vision if researchers can chip away at those challenges we discussed?
The vision is definitely AI that can genuinely help us more effectively in the real world. Robots in our homes that can actually do chores reliably, smarter systems in factories, safer autonomous vehicles on our streets. The work now is really focused on bridging that sim-to-real gap further, making the virtual worlds look and act even more like reality, while still keeping all that crucial readable data intact. And as we mentioned, a huge push is towards standardizing things, getting the global research community to agree on common formats, common ways of describing these worlds, so everyone can build together more easily.
So smoother collaboration is key.
Absolutely. So I think in the coming years, as these worlds get better, more standardized, more realistic, we're going to see AI learning in ways that feel much more, well, human-like in some respects. Learning through reading the textbook, practicing diligently, getting that immediate feedback, and becoming competent before they have to deal with the full complexity of our messy, unpredictable, real world. It's about building intelligence on a really solid foundation.
That's fascinating. It really makes you think, doesn't it?
Yeah.
You know, if we humans had our own kind of machine-readable world for learning new skills, imagine trying to learn, say, surgery or flying a plane in an environment where every single rule, every object, every possible consequence was perfectly laid out, and you could get instant, precise feedback. How much faster could we learn? It sort of opens up thoughts about human learning too, doesn't it? Anyway, that's perhaps the thought to leave with our listeners. Thank you so much for joining us and walking us through this really exciting area.
My pleasure. It's a truly fascinating intersection, isn't it? Virtual worlds, data, intelligence, artificial and human. Lots to keep thinking about. Definitely encourage everyone listening to stay curious. Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.